Video, we're going to do a quick review of factoring. And factoring is going to be important because in the next couple sections we're going to be solving a quadratic equation, and factoring is going to be one of the strategies that we use. Okay, so I like to divide my factoring up into about 4 different categories. The first category would be the greatest common factor. I usually put this one first because this is the best type of factoring to try to do first. If there is something in common between each of the terms that you have, in this example right here we have 2 terms. Terms are either added or subtracted. Anything that they have in common, we can factor that out to the front, and that makes the rest of our factoring a little bit easier. So for the GCF, you're going to look at both the numbers and the variables. If we start with the numbers, we are looking for the biggest factor that 3 and 12 have in common. When we say biggest, we're looking for the biggest number that divides evenly into 3 and into 12. So in this case, that would be 3. 3 divides evenly into both. Then we would look at the variables. We want to take the highest power of each variable that they share. Or I guess I should say the highest power that they have in common. Okay, so this first term has 2 x's, the second term has 1 x, so what they have in common really between both of them is just 1 x. And then we write that outside the parentheses. Essentially, we're dividing by 3x, and we're going to write what's left inside the parentheses. So when I divide this by 3x, I have an x left over. When I divide this by 3x, I have a minus 4 left over. So that's factoring using the greatest common factor. The second category goes well with the GCF because it is sort of like 2 steps of doing the GCF together, and this is factoring by grouping. So factoring by grouping works the best when you have 4 terms. That's really when this method is applicable. Okay, and this is the basic process. We're going to take those 4 terms and group them into pairs, and then we're going to factor out the common factor in each pair. When we do that, that leaves us with 2 rather large looking terms that we'll say because they're added together or maybe subtracted. And then the parentheses that we see in each of these 2 giant terms should match up. And if they do, we can do grouping. And then we're going to factor out that matching parentheses. Let me demonstrate that for you so you can get a better idea of what it looks like. So here's an example. We have 5x squared minus 10xy minus 3x plus 6y. So you can see the 4 terms. We're going to group them into pairs. Now you're welcome to move these around if you think that would be advantageous. I've never really found it to give me a huge advantage, so I don't usually move them around, but you can. Okay, so I'm going to group the first 2 together. Anytime I have a minus in the middle, I'm going to attach that to this 3, make it a negative 3x, and I'm going to put a plus in between the parentheses. The reason for this is because if I were to put the minus in between the parentheses, by writing the second group of parentheses here, I'm saying I've factored out a negative, and I may not be ready at this point to do that. Then I'm going to look for the GCF in each pair, just like we were just practicing. So 5 and 10 have a 5 in common. 5 divides evenly into both. We have an x squared here and an x times y here. So in common, they both have 1x. And then I want to write what's left over if I were to divide by 5x. So I have an x left over from the first term and a 2y left over from the second term. Then I want to look at the greatest common factor between the second pair. 3 and 6 they have a 3 in common, and I'm going to use -3 because I would like my leftovers here in the parentheses to match. So if I use -3 and I divide, I'll have an x left over. 6y divided by -3 would be a -2y. Okay, notice now that these two parentheses are the same. So the second round of GCF, you could sort of think of these as two really large terms if you wanted to. They both have that x minus 2y in common. So we're going to factor that out. And then the little pieces out front go together to make the second factor. And that's factoring by grouping. You can always reverse the order of these two parentheses if you would like, right? They're multiplied, so we can multiply in any order. That's fine to do. Okay. The third type is factoring binomials. I always save the trinomials for last, okay? So binomials, these would be polynomials with two terms. There's actually several types of special factoring that fall into the binomial category. The difference of two squares is one of them. Also, the sum of cubes and the difference of cubes, those would fall into this category as well. I usually leave those out in college algebra. The cubes, we usually use a formula to factor them, and I usually give you practice with that if you've taken me for intermediate algebra. So we're going to stick with just the difference of squares this time. The difference of squares are unique because there's no middle term here. Difference indicates that there's a minus. And that's going to happen when we have two almost identical looking parentheses, but one will have a plus and one will have a minus. Okay, and you could do some foiling here just to check that this identity is true, but it definitely is. Those outside and inside terms are opposite in sign, and so they would add to 0. So we could do the same kind of factoring here. The key maybe is to recognize what 36x squared is the perfect square of. So I'll write that step here. You don't have to write that step out. Maybe this will just put on paper what we would think about doing in our heads. 36x squared, that's 6x squared. So that's the perfect square of 6x. 25, I know that's the perfect square of 5, right? 5 times 5. So if I compare with this formula, right, 6x is sort of playing the role of x, 5 is playing the role of y, and I'm going to have two parentheses, one with a plus and one with a minus. Okay, and that's called the difference of squares. The last category would be the trinomials. Trinomials would be polynomials that have 3 terms. There's several different strategies you can use to factor trinomials. Usually when we think of factoring, this is what we think of, right? So there's a trial and error method I want to show you, and then there's also an AC method, so I want to show you that in case you're interested. There's lots of visual type diagram types of methods that you can use for factoring trinomials. Whatever you have learned in the past is fine to use here. I don't want to change what you've done in the past. If you don't have a method, I want to give you a look at what I use, okay? But if you have another method, I'm happy to go with that. So one method is to kind of reverse the process of FOIL. FOIL is where we multiply polynomials together. This stands for the first, the outside, the inside, and the last. So when I multiply things out, the first times the first turns out here in the front. The last times the last shows up here in the back. And then very often the outside and the inside are like terms, right? They have the same variables to the same powers, and so we add them up to this middle term. I always start out with this one because it's super simple, just to give you the basic idea. So we have two parentheses with two things in each parenthesis, and the first times the first should multiply to be x squared. Since we would like a variable in each parentheses, x and x is the most obvious choice. Then we need numbers in the back that multiply to be 2 and add outside plus inside to be 3x. I always start with this one because there's only really one option, right? 2 times 1. 2 times 1 would be 2. On the outside I'll have 2x. On the inside I'll have 1x. So those will add up to be 3x if I make them both positive. So that's kind of the process I go through when I factor. So here's one that's maybe a little less obvious. So again, I'm starting with x squared, so that tells me I need an x and x. And then I'm looking for two numbers in the back that multiply to be 15 and add to be -8. Think for a second, what numbers multiply to be 15? And then do those numbers add up to be -8? Okay. Maybe you've already figured it out. 5 and 3 work really well here. 5 times 3 is 15. And then on the outside, if I wrote it out, on the outside I have I would like to have a -3x, right? And a -5x, so that they will add up to be that middle term. And in order to do that, I need two negatives. Just to point out here, you can always check your work by multiplying these back out. Right? So if we were going to do a quick check, I don't usually do this, but on a test it might be important. X times x would be x squared. On the outside, I'd have -3x. On the inside, I'd have -5x. And then the last times the last will be +15. And if I combine this in the middle, I get what I started with, and that's a good sign. Okay, now things change a little bit if we put a number in front of the x squared term. In this case, it's n squared. So we could still use trial and error. I actually want to show you two methods for this one. If you use the trial and error method to multiply to be 2n squared, one parentheses needs an n, a 2n, and one parentheses needs an n. Okay, I should have probably said this at the beginning. There's no GCF here, right? No number divides evenly into both 13 and 6 or even 2. So for that reason, the 2n must be inside the parentheses. All right, then I need two numbers in the back that multiply to be 6. Now these numbers by themselves do not add up to be 13 because the 2 is going to play a part. Right, and we could try a bunch of options. I like to draw these rainbows sometimes. Okay, so 6, it could be 6 and 1, or it could be 2 times 3. We could try a bunch of things. It's hard to teach the trial and error method because nobody really wants to see the wrong answer. Okay, so you could try a bunch of things. If it didn't work, you could cross it out. I think what's going to work for us is if we do 6 and 1, I put a 6 here and a 1 here. Where I place these numbers makes a difference. Right? If I'm putting the 6 here, it's going to give me something different on the outside than if I were to put it right here. because of the 2. The parentheses are not equivalent anymore. So if I put the 6 here, then 2n times 6 on the outside will give me 12n. And 1 times n on the inside will give me 1n. I want to make these add up to 13n. So I think I can do that if I make them both positive. Okay, let me show you the AC method for this same problem in case you're interested. So this was the trial and error method. You try stuff out. If it's wrong, you try something else, right? That's sort of the idea. All right, the AC method is a little bit more systematic than sort of a guess and check. The AC method is based on the idea that we have something in this format, ax squared plus bx plus c. So this 2 would be the a, 13 would be the b, and 6 would be the c. So we want to take a times c. For this particular problem, that's 2 times 6, so that would be 12. And the way this method works is we look at all the factors of 12, and we use that to break up this middle term into 2 parts. So we want to look for factors of 12. I'm going to list them all out even though I think we got our answer right away. We're looking for factors of 12 that add to 13. So I always go down the list. Okay, 1 times the number. Okay, if 2 goes in evenly, for this one it's 2 times 6. Then I go to 3. All right, if this were not a 4, I would keep going. But once I get to a number that's on the other side, I know I've listed all of them. 3 options. I want to pick the one that adds to 13. That would be this one. And then I want to rewrite this as 2n squared plus 1n plus 12n plus 6. And then now that I've broken that up, I have 4 terms and I can factor by grouping. So because I have a plus in the middle, I'm going to be a little lazy and just throw on my parentheses. Okay, and the GCF for the first pair would be n. And we'll have a 2n plus 1 left over. The GCF for the second pair will be 6. And I'll have a 2n plus 1 left over. Here's my 2 giant terms. Notice the parentheses match. If the parentheses did not match, we would be stuck and we couldn't finish the grouping method. But they do match here. So 2n plus 1 is one factor, and n plus 6 is the second factor. Notice we got the same answer here as we did with the trial and error. All right, well that wraps up all the factoring. I hope you have a chance to take some time and practice your factoring, as we will begin to use it soon to help us solve equations of the quadratic equation type. All right, good luck.